All right, PCH. As you guys know, today's lesson is going to be a review of systems of linear equations, but with a specific focus on how these questions show up on the SAT and the best practices and strategies that we can use in order to attack these problems most effectively when they come up on the test. And so we already had a discussion as a part of our Do Now as to what even is a system of equations. And so my next question for you is, how many ways do we know to solve a system of equations? I'm sure most of you are able to remember that, yes, we know 3 different ways to solve systems of equations. And hopefully a few of you are even able to remember one or more of these methods of solving. And so you can see on my screen in green that the 3 methods we know are substitution, elimination, and graphing. Let's go ahead and do some examples. We'll start out with substitution. Now, when we're trying to solve by substitution, essentially what we're looking for is for one of our 2 equations to be either x equals something or y equals something. And we see that for this example, our second equation is y equals negative 3x plus 15. The reason that we're looking for an x equals or a y equals for one of our equations is because whatever it's set equal to, that's what we're going to be plugging in or substituting for that variable into our other equation. And so I'm going to go ahead and do that now. I'm going to be plugging in our second equation into our first equation here. And so again, all I'm doing here is substituting negative 3x plus 15 in for y in our first equation. And this is key because what we notice now is that our first equation is in terms of only one variable. It's only in terms of x, and that allows us to solve for x. And so when we distribute, we're left with this, and I am curious what you all might get for x. Yep, after combining like terms, dividing by 13 on both sides, we get that x is equal to 4. Now the last thing we need to do is solve for y, and the really nice thing about substitution is that in order to get to this point, we already had to have had an equation of y equal to something, and that's our second equation here. And so all we have to do is plug in x equals 4 into this equation. Yes, when we solve for y, we get y equals 3. And as our solution, we get the point 4, 3. Let's move on to elimination. So when we're trying to solve a system through elimination, ultimately what's happening is we are combining our 2 equations, either through addition or subtraction, and through that process, one of our variables is canceling out. Now I've already started some of my work here so that it can be easier to apply the words that I'm saying to an actual problem. And so, again, ultimately what we're doing is trying to combine our 2 equations together so that one of our variables can cancel out. And I noticed that, okay, when I'm looking at the coefficients in front of my x variables in both of these equations, I see that 4 is a multiple of 2. And so if I multiply this entire first equation by negative 2, that's going to give me this equation down here. Now, again, the reason I multiplied by a negative 2 was because when we are combining these equations, and I'm going to do that through addition, these x variables now are going to cancel out because a positive 4x plus a negative 4x is 0. And so our x variable goes away. Then we get a negative 4y is equal to a negative 12. and then when we solve for y, we get y is equal to 3. And this is actually really similar to substitution in the fact that what we end up with is an equation that's just in terms of a single variable. And what this allows us to do is exactly what we did, solve for that variable. And the last thing we need to do is find our x value. And so I'm going to plug in y equals 3 into our first equation. And after a little bit of algebra, we get the solution to our system of equations here to be the point 7, 3. So we are ready to move on to our final method of solving, which is graphing. And you'll notice that this system is actually the same system we just solved for in our elimination example. And so when I think about graphing, especially when I'm trying to do it by hand, ideally I want my equations to be in slope-intercept form. And so I went ahead and put both of my equations into slope-intercept form. Now when I look at these equations, and they're the equations that are starred, if I think about trying to graph these by hand, yes, I can do it, but it really is not going to look pretty for me. Like I have a y-intercept of 23/3 and another one of 17, and I have to graph these lines and then find out where they intersect. That's going to be kind of a pain. And so for sake of time and for sake of ease for our notes today, I went ahead and graphed this on Desmos. And you can see that when these lines are graphed, their point of intersection, which is our solution, is the same point that we got when we solved by elimination of 7, 3. Now the reason I had to solve the same system of equations using two different methods is twofold. Point number one, I wanted to stamp for us the fact that any system we have can be solved using any three of the methods. And that's just how it is. Point number two, and most importantly, we notice that when we go back to our work, especially when we're looking at elimination, honestly, the work wasn't too bad. Once we got our equation set up to eliminate the x variable, the math was super easy, and it didn't take too much time. When it came to graphing, honestly, I wasn't really feeling even putting the equations into slope-intercept form. And of course, we didn't even have the time in class today to actually go about graphing these two lines by hand. And so point number two, a lot of the times, there is going to be a more efficient way of solving a system of linear equations. In this case, it was much more efficient for us to solve using elimination than by graphing. And we know that on the SAT, time is money. We need to use our time as wisely as possible, and so we need to look at some strategies that we can use to look at our systems of equations before we even start the problem and say, hey, what is going to be the most efficient way for me to solve this system? And you'll see those strategies right here. Okay, PCH, we've had some time to talk about strategies to figure out which method of solving is going to be most efficient for a given system of equations. And so now we're going to shift gears a little bit to another tool that will help us save time on the SAT and work smart, not hard. And so that's going to come in the form of solution possibilities. When we have a system of just two linear equations, which is what it's always going to be like on the SAT, you have three possibilities for your number of solutions. You can either have one solution in which your lines are intersecting, no solutions in which you have parallel lines, or infinite solutions in which you have two equations that represent the exact same line. And you can see each of those situations again represented in this chart on the Ed puzzle. Now, wouldn't it be cool if we could look at a system and before doing any math, determine how many solutions the system might have? I'm here to tell you that there is a way to do this, and we're going to work through that right now. And so you'll notice, again, if we have one solution, our lines are only intersecting at one point. And something that is always true if our lines are intersecting is that our lines have different slopes. And so when we are looking at our system, if we can determine what the slope of each of our lines is, if they're different, we know we're going to have one solution. No ifs, ands, or buts. Now, what we notice with no solutions and infinite solutions is that both of these have the same slope. So how are we supposed to determine whether a system of equations has no solutions or infinite solutions? Exactly. We are looking at the y-intercepts, and we see that when our system has no solutions, our lines have different y-intercepts. But when we have infinite solutions, it's the same line. They have the same slope, and they have the same y-intercept. Okay, so let's try a few problems that show us how the SAT might test our understanding of this concept, of understanding solution possibilities. And so when we're looking at number 1, it gives us a system of equations with a constant k, and it's asking us what value of k is there no solution for this system. And that is really where we are trying to focus our attention, because if we remember from the notes we just took, a system that has no solutions has the two equations having the same or equal slopes, but different y-intercepts. So y-intercepts that are not equal. Their first equation is written in standard form. We just talked about on Tuesday that there's a special way for us to find slope of our line if it's in standard form. But yes, the slope of our line in standard form is negative a over b, and for this specific equation, we get 6 over 5k. Now the second equation is going to be a little bit easier because it's in slope-intercept form, and so we know that our slope is equal to 3. Again, for a system with no solutions, we need these slopes to be the same, and so we're going to set 6 over 5k equal to 3 and solve for k. When I solve for k, I got it equal to 2/5. And the nice thing about a problem like this is that if they're asking for a value of k for which there are no solutions, they're not going to give you two equations that are going to have the same y-intercept. And so I went ahead and wrote the y-intercept for both of these equations on the screen. But technically, as long as you get that value for k, you are good to go. You shouldn't have to worry. Now for the second example, I've already done the work. My answer is starred at the bottom right corner of the screen. Do you notice anything about my answer in the set of equations that they've given us? Hopefully you notice that if you're looking at the second equation, a over b is negative 3 over negative 7. That gives us 3/7. The question asks us, or tells us actually, this system has infinitely many solutions. These equations represent the same line. And so did I have to do all this work? No. I could easily recognize the fact that, okay, yes, infinitely many solutions means that these equations represent the same line. And so I can just pull a over b from the second equation, that negative 3 over negative 7. Again, it is so important that we are working smart and not working hard. All right, that's the last example that we are going to do as a group. And now we're going to head over to Delta Math to do some more practice.